Tiffany, and this is Crash Course Physics, Student Edition. And today we're going to look at the heart of classical mechanics, Newton's laws. Stan, stop dropping apples, this is a serious topic! Anyway, Sir Isaac Newton was born in England in 1643, one of the greatest scientists and mathematicians up to date. In fact, he was a Sir since Queen Anne knighted him in 1705 for his contributions to the intellectual world. His three laws revolutionized the way people studied physics, but more on that momentarily. Newton went to Trinity College in Cambridge, where he became interested in math, physics, and astronomy, and began writing a journal, in which he wrote his revolutionary concepts, including gravity, diffraction of light, and most importantly, his three laws of motion. The first law, also known as the law of inertia, states that an object in motion will stay in motion and at a constant velocity, and then an object at rest will stay at rest, unless acted upon by an outside force.
Miss Tiffany, that's not true! A ball will stop rolling if I'm not pushing it anymore.
Oh, me from the past, stop trying to be smart. There are many other forces that act on the ball in the real world, such as friction. If you tried that in a vacuum, the ball would continue rolling, but you would definitely die. Remember, in the absence of a net force, an object will simply move in the same direction with a constant speed unless any other force acts upon it. Basically, this means that nothing can accelerate unless a force is applied to it, either in the positive direction to speed up or in the negative direction to slow down. Let's go to the example you brought me from the past. Unfortunately, I can't actually go into a vacuum, so I'll have to settle with a nearly frictionless surface, such as ice. After the initial applied impulse, the ball moves at a constant velocity on the surface for a pretty long time. On the other hand, if the ball is rolled on the surface where there is a force of friction acting in the opposite direction of the movement, in which the friction is greater, such as on a rough carpet, then the ball quickly decelerates, eventually coming to a stop. That's fine. Okay.
I feel like it's recording. It's recording.
Oh, it's recording. Oh, is it time for the open letter? Alright, but first, let's see what's in the secret compartment. Oh, how lovely! A cube of ice! An open letter to ice. Dear Ice, thank you for being literally the only surface on which people can actually do experiments without having stupid friction intervening. I know that the world basically runs on friction, and without it, we would all just be gliding around the world without ever stopping. But seriously, Newton's laws are based on the ideal experimental world, and in the ideal world, there is no friction ruining experiments. Of course, there is a bit of friction, but it may as well be negligible, since when objects come into contact with ice, a thin layer melts, and the object slides on a layer of water. Ah, ice, you're such a great resource for physics. It's unfortunate we live in Campbell, the land of no ice and little rain. Best wishes, Tiffany Green.
But back to Newton's laws. The second, and arguably the most important, is that the acceleration of an object as produced by a net force is directly proportional to the magnitude of a net force and inversely proportional to the mass of an object. Essentially, force equals mass times acceleration. Since the formula is a vector equation, force and acceleration must travel in the same direction, which is why, in kinematics, force must be divided into the x and the y axis. The motion also changes in the direction the force is applied. Of course, this equation has many different derivations that are used in different parts of physics. For example, the rotational derivation of the second law is torque equals moment of inertia times angular acceleration. A slight tangent, Newton also invented calculus, which he used to justify many of his physical laws. The original equation Newton wrote was that force equals momentum divided by the change in time. You can convert this equation into the normal one, since momentum is mass times velocity, but the original equation is actually the derivation of the common equation, since the integral of velocity is acceleration. The second law is the most important when it comes to projectile motion, since in these equations acceleration equals negative gravity. The derivative of that is v equals gravity times time plus c. When t equals 0, c equals v initial, so v equals gravity times time plus v initial, which can be translated to v equals v naught plus at, which is a kinematic equation. Okay, let's go to the thought bubble. If Tim, who weighs 50 kilograms, is skating in a rink and bumps into Stan, who weighs 80 kilograms, yes, Stan, you're gonna be the fat one. They push against each other with the same force regardless of their difference in mass. However, back to Newton's second law, since the force is the same and their masses are different, they move with different accelerations after the collision, which makes sense since it is expected that Tim, the lighter one, will be more affected by the collision. Since the forces are equal and opposite, Tim and Stan move in opposite directions away from each other. Then there is the connection to cars. According to Newton's third law, as a car's wheels spin, they push with a backwards force on the road. Newton's third law states that the road must react with an equal and opposite force, pushing the wheels forward with the same force and allowing the car to move across its surface. Ultimately, Newton's three laws created what is now known as modern physics. Of course, prior to Newton, there were other scientists that furthered physics from the authoritarian grasp of the church, like Copernicus and Kepler, and many of these scientists did influence Newton in his work. However, it was due to Newton's genius and relatively modern time that he lived in that allowed his complete revolution of physics, allowing us lesser human beings to learn from his findings and expand on his ideas. Thanks for watching. I'll see you next year.